Okay, guys, let's start with some announcements or reminders. So you turned in the homework yesterday. We had extended it to Sunday. You have the project proposal due on Wednesday. That's what we call milestone 1. Let me just say a few words about that. That doesn't have to be super extensive. It's just, I think we said 2 pages is all you're supposed to fill out. And you can't get a bad grade in the project proposal if you write a project proposal. The only way you can get a bad grade is if you don't write one. It's essentially just a forcing function for you to get stuff down on paper. We're not grading it on content. Now, that said, the more detailed you make it, the more useful feedback you'll get right away. So if you're not sure about the project direction, then put effort into it and we'll give you some feedback. So don't stress out about that. Just put something down and turn it in. We're going to, after the project proposals are in, we're going to actually assign every group to a TA mentor. So you'll have one of the 5 TAs that we have is going to act as the mentor for your project, and then that person you can check in with as regularly as needed throughout the semester for help, and he will try to guide you if he feels like your project is maybe not pointing in a direction that it should. Okay, so that's what that process is going to look like. Any questions about the project proposal, actually? Yeah.
As far as like permissions,
Yeah, you can ask POA for that. Yeah. Okay. So the next reminder was that your homework 3 is due 2 Fridays from now. So not this Friday, but the Friday after. It'll be released, I think, probably now. We've finished writing it, and I think it's going to be up sometime between now and the end of the lecture. The TAs will release it. So because you have a bunch of stuff crammed into this short period of time, like we have a shorter homework cycle, and you have your project proposal due, and just generally, I don't want you guys to be crushed by the homework. I have some good news in that we're going to shorten it to 3 questions. So the way that we're going to do it this time is there are 4 questions on the homework. You're required to do questions 3 and 4, and you can choose one of questions 1 or 2. Okay, so you can write them both if you want, and then we'll just take the higher score, or you can just do one. So there'll be a Piazza post confirming that, but that's the plan. So you just choose either question 1 or 2, and then do questions 3 and 4. Okay, so hopefully that'll be manageable in the kind of shorter cycle we have this time. Okay, so today we've graduated. We've moved on from our algorithms unit. So we've done like a basic theory unit on convexity, essentially. We've done a first order algorithms unit. And now we're doing a duality and optimality unit. So it's our second theory unit. And we're starting with duality, specifically in linear programs. And maybe just an editorial comment. I think duality is an absolutely beautiful subject. When I first learned duality, I was like, it seems okay. But over time, as I've gotten to understand it better, I think it's a very deep idea that leads to a lot of important, powerful conclusions, and it's very simple. So this is one of the, I think we've seen this already a couple times in the class, and we'll continue to see this. These are concepts that are mathematically very simple. We're going to construct the more general Lagrangian form of duality next lecture, and the KKT conditions after that. All of these arguments are actually fairly simple, but they lead to very deep conclusions. So just a reminder about what we talked about last time. Very quickly, we talked about stochastic gradient descent, the setting being that we want to minimize an average of functions, and SGD, or stochastic gradient descent. It looked like gradient descent, but we replaced the gradient of this entire criterion, which would be an average of the gradients of these functions, by an unbiased estimate, which was gotten by just sampling one of these functions and taking its gradient. So IK is chosen uniformly at random over 1 through m. And so this functional form fits things like regression, logistic regression, all sorts of regularized maximum likelihood problems, etc. So it's a very kind of common form that you'll see in machine learning applications. And if m is large, which in our machine learning context would be the number of data points, usually call it n, then this update is going to be a lot more efficient than taking the full gradient. So that's why SGD has such a large role in machine learning these days. We talked about step sizes chosen to be fixed and small, which, like the subgradient method, actually would not guarantee conversions, or diminishing, in which case it would guarantee conversions. Compared to full gradient, it's much cheaper in terms of the iteration cost, but it can be slower in terms of the iteration complexity, so the number of iterations it takes to converge. And we saw that it attains suboptimal rates. Notably, it doesn't adapt to, for example, strongly convex functions. If you apply gradient descent to a strongly convex function, let's say we additionally know that function has a Lipschitz gradient, then we get a very fast linear rate of conversions. SGD would not. It would be stuck in the sublinear regime. So we get something like 1 over k rather than c to the k, where c is something less than 1. So that's a fact about vanilla SGD. And I claimed it could be improved by variants that we might revisit later if we do an advanced topic lecture on it. I'm not positive, but if there's sufficient interest, then we might do a whole other lecture on that. Okay, so let's jump right into duality. And the way that I like to introduce duality is to talk about linear programs. So we're just going to talk about linear programs for almost the whole lecture. And I like talking about duality in linear programs because it's constructive. So we're actually going to construct the dual through very kind of simple natural process. And you could use what we learned today to construct duals for linear programs as you go forward. It's an alternative viewpoint than Lagrangian duality, which is more general, that we'll mention today and then focus on next time. So how you treat linear programs from here on out is up to you, either in this way or the more general way. But let's suppose that our goal for the moment is to find a lower bound on the optimal criterion value. Okay, that's the goal. Let's say that is the goal in duality. Why that's useful, we'll see why that's useful when we talk about optimality. But for now, let's just say you can trust me, that it's a useful thing to find a lower bound on the optimal value in your problem. So in other words, you have some problem, which is minimize some function f of x. We want to find some b that lower bounds the optimal criterion value. Okay, and obviously we want the tightest b possible. We don't want to just pick any b. We want a pretty good lower bound. So here's a super simple example, which is the following linear program. I have univariate x and y. I'm minimizing x plus y subject to these two linear inequality constraints. X plus y is bigger than or equal to 2. X and y bigger than or equal to 0. Okay, if I asked you for a lower bound for the criterion value in this problem, you would say 2, because that's this constraint. This constraint tells me that x plus y must be bigger than or equal to 2. So of course that's going to lower bound the optimal criterion, right? So that was, such a vacuous example. You might think that we just got lucky and there's not much to this, but actually there is a little bit more to this. So let's just try again. And I'm going to kind of do these in the doc cam, but the information is also in the slides. So I'm going to just modify the example a little bit. So let's suppose my LP is now x plus 3y, okay, subject to the same constraints. Okay, how would I get a lower bound out of these? Well, I'm going to recognize that y being bigger than or equal to 0 actually implies the following constraint, 2y being bigger than or equal to 0. Okay, obviously. And in addition, if 2y is bigger than or equal to 0, and x plus y is bigger than or equal to 2, then I can also write that I can add these two and write that x plus 3y should be bigger than or equal to 2. Okay, so I've generated constraints, in this case by multiplying one of these constraints by 2, and in this case by adding this constraint with this one. And therefore I get the same lower bound. Right? I've been able to basically create a constraint that says that my criterion value should be bigger than or equal to something. So this is also going to be true at optimality. So the lower bound is still 2. Okay. So just to continue on with the practice, but now making it a little bit more general. Okay, let's suppose my criterion value was px plus qy. I had the same constraints, x plus y being bigger than or equal to 2, and I had x and y being bigger than or equal to 0. Okay, now I can actually generate, let's say, a set of new constraints that are going to hold additionally by fixing any arbitrary a, b, and c that are non-negative, multiplying this first constraint by a, right, both sides by a, so I get that ax plus ay is bigger than or equal to 2a. That's a valid constraint for any a that's non-negative, right, following just by multiplying this one. And I can also say that bx should be bigger than or equal to 0, and cy should be bigger than or equal to 0. And all these constraints hold. And now let's suppose I add them all up to generate another constraint, which is going to be a plus bx plus a plus cy is bigger than or equal to the right-hand sides when I add them all up, which is 2a. Okay, so just again, a quick recap. I've multiplied these constraints each by non-negative parameters, a, b, and c. Consider them fixed for now. I've written out the corresponding inequality constraints. I've added them up to get this inequality constraint. These are always valid constraints. They just stem from these. And if I could find a, b, c that are non-negative such that a plus b is p and a plus c is q, then the lower bound on the criterion of this linear program is going to be b equals 2a. Right? Because then I would have px plus qy is bigger than or equal to 2a. So that's my lower bound right here, 2a. Okay, so in other words, we could say, I've written here, the lower bound is 2a for any triplet a, b, and c, such that a plus b is p, a plus c is q, and these three are all non-negative. So let me just quickly pause, because this is kind of a this is a key thing to understand. See if there's questions. Okay, so that's a lower bound. You might ask, what's the best lower bound? What's the very best lower bound I can get? Let's say with this problem. Okay, the very best lower bound I could get is actually to form another optimization problem, which just maximizes 2a, the lower bound, subject to these constraints. Right? So any a, b, and c that are non-negative, for which a plus b is p, a plus c is q, gives me a lower bound of 2a. The best lower bound is the maximum of 2a over all a, b, and c that are non-negative, such that a plus b is p and a plus c is q. That's the best lower bound. So actually, somewhat coincidentally, at least at this point, this problem is also a linear program. So finding the best lower bound to our linear program has given rise to another linear program. And this is what we call the dual linear program. And in this kind of context, we call the original one the primal. Okay, so just by simple direct arguments, we've essentially constructed a dual to this problem that all we know at this point is that at optimality, this linear program is going to have its criterion value less than or equal to this one. Okay, some notes. The number of dual variables is by construction the number of primal constraints. Right? So I defined A to be a multiplier for this inequality, B for the inequality on x, and C for the inequality on y. So I've got one dual variable. That's these things, A, B, C. per primal constraint. Okay, so here I had 2 variables and 3 constraints. Here I have 3 variables, right? 1 for each constraint. It's a question.
Yeah. In your example, isn't it sufficient to have A plus B less than B to have a better lower bound on the problem?
Yeah, you're saying you can eliminate B from the dual linear program.
Has not the equality constraints, but less than equal.
Yeah, that's what you say is correct, but that's just eliminating one of these variables. So it doesn't really change the problem. It's just you simplified the dual. That's it, right?
Doesn't this imply that all those less than equal to constraints have to be tied in the dual, but not necessarily in this case always?
I'm not sure what you're saying. What implies that? But I guess the answer to when constraints will be tight will be answered by the KKT conditions. So when we learn about the KKT conditions, we're going to learn about a condition called complementary slackness, which tells us when conditions have to be tight. So we'll get a precise understanding for that. Okay, so that was one note. I guess one other note, and then one question I'll pose to you. So the note is that, or I guess let me say there's 2 questions I'll pose to you. I'll make them both questions. The first is, what if there is no A, B, and C that satisfies these constraints? Okay, what happens if I picked, for example, P to be negative? If P was negative, right, then I can never find positive or non-negative A, B, and C such that A plus B is P. So what would happen here? What would my lower bound be? Yeah. Right. It would just be negative infinity because essentially these constraints would not be feasible, and maximizing over the empty set gives us negative infinity. Right? It's the worst possible value, negative infinity. Minimizing over the empty set we think about as giving us infinity. Maximizing over the empty set gives us negative infinity. So it's a trivial lower bound. Right? So we haven't assumed anything essentially in forming this dual. If these constraints cannot be met, then the lower bound is minus infinity. Okay, let's actually go to that case. So I said that was a trivial lower bound. But what happens if P is negative in this problem here? What do we get for the criterion value in this problem if P is negative? We get negative infinity, right? Because I could take X to be, let's say, arbitrarily large, positive, satisfies these constraints, doesn't matter what Y is. I could set Y to be 0. And I could drive the criterion to minus infinity. So in that case, that trivial lower bound was actually still equal to the primal criterion value. So it was not loose. It was not like this was finite and this was minus infinity. It was actually tight. So that leads us to the second question, which is maybe we can just do a show of hands. How many people think that this construction is going to give us something tight in general? Okay, and how many people suspect that it can be loose? Okay. So interestingly, with linear programs, the dual is essentially always tight. So the dual lower bound is essentially always tight. It's only for very pathological linear programs that it's not tight. So it can happen, but it's for kind of very pathological cases. And I think it's the next lecture. The next lecture will... Or no, you'll have to wait 2 lectures until we talk about the KKT conditions, I believe, in order to figure out, or next lecture, I can't remember which one I do it in, but soon you'll figure out when the conditions under which the dual will be tight. And we'll see that for linear programs, the answer is pretty much always, except in some pathological cases. So I just did another one. Okay, this one's nice to go through. It's instructive because we actually have inequality constraints. Let's just quickly do that in the primal. So we'll just kind of quickly run through this. Our constraints are x bigger than or equal to 0, y less than or equal to 1, and 3x plus y equals 2. So I'm going to, let's say, fix a and b that are non-negative, and I'm going to write this as ax bigger than or equal to 0. So this one I'm going to actually rewrite as minus y bigger than or equal to minus 1, just so that I can multiply both sides by b, which is non-negative. I think that's just a kind of consistent way of handling inequality constraints. And this one, I'm going to fix a parameter c, but actually c is not constrained to be non-negative, because I can multiply this equality constraint by any c, and it'll continue to hold, even if c is negative. So for the inequality constraints in the primal, we are forced to take non-negative dual variables. And non-negative, once we interpret these to be, let's say, properly oriented inequalities. For the equality constraint, there's no constraint on the dual variable, on its corresponding dual variable. So I can just take, 3cx plus cy equals 2c. And that will be true for, this will hold true for any c. So I can add all these together, right, as per my usual trick. Collect the stuff on x. That'll be a plus 3c x plus, I guess it's c minus by is bigger than or equal to 0 minus b plus 2c. So that's my lower bound in the criterion, provided that this thing is equal to p and this thing is equal to q. Right? And that forms my dual problem. I'm going to maximize this lower bound, 2c minus b, subject to a plus 3c is p, c minus b is q, a and b are non-negative, and no constraints on c, on the sign of c. Okay. So here's an outline for the rest of the lecture. We're going to talk about duality and kind of general form linear programs, not just like very simple ones like this. And I'll talk about max flow and min cut, which is a nice application of LP duality. I'll go through this not as carefully as the last example, because this one is visited more carefully on your homework, so you can see the details there. Then we're going to do a second take on duality. So this is Lagrangian duality, which is actually significantly more general than what you're seeing now. And we'll finish with, I'm hoping to get to treat this example more carefully. It's a very interesting application of LP duality to kind of a very simple problem in game theory called matrix games. So let's start with general form linear programs. So here's a general form LP. Okay, I'm minimizing C transpose X. X is a vector here, subject to AX equal B and GX less than or equal to H. So this is interpreted component-wise, as we usually do in this class. Okay, and just like we did with these simple kind of two-variable LPs, we can form a dual to this. And we're going to follow the same logic, okay, which is we're going to pick any vector u and any vector v that's component-wise non-negative. And the length of v is going to be equal to the number of inequality constraints. And the length of u is going to be equal to the number of equality constraints. Okay, and we're going to, so the way you can think about this is that we have a bunch of equality constraints, I transpose X equals BI, and a bunch of inequality constraints. GI transpose X is less than or equal to HI. And I'm going to do the same thing, which is I'm going to basically take a bunch of UIs that are anything, and a bunch of VIs that are non-negative. And I'm going to just form new constraints by multiplication, let's say for the equality constraint by UI. So I get UI times AI transpose X equals BI times UI. And for the inequality constraints by multiplication by VI after reversing the sign, right? So I'm going to say that minus VI times GI transpose X is bigger than or equal to minus VI HI. Okay? a more succinct way of writing this, right, if we had ax equals b and gx less than or equal to h, a more succinct way of writing actually the sum of all these inequality constraints, right? If I sum these all up, then I can express it all in terms of inner products, right? I can take an inner product of both sides with u and get that u transpose ax equals u transpose b. And I can take an inner product of both sides with v here, which is again equivalent just to summing these up over all I, to get that minus v transpose gx should be bigger than or equal to minus v transpose h. Okay, so this is, I think, just a more succinct way of thinking about it when you have vector variables. And, okay, well, I can, again, just generate new constraints from these by let's say, adding these together. Okay, so I can say that, let's say v transpose gx minus h plus u transpose ax minus b must be less than or equal to 0. That I just get by adding these constraints together. Okay, so we've repeated the same steps, which is we've multiplied the inequality and equality constraints by dual variables. We've added them all together, and this is what we've gotten. This one inequality, v transpose gx minus h plus u transpose ax minus b is less than or equal to 0. That's what I'm starting with right here. So another way to read this off directly is just to say, well, at optimality, this is 0. Or actually, just for feasible points, this is 0. So that then I can multiply by any u. This is going to be 0. And this is going to be negative in every component. So if v is positive in every component, then this thing is going to be also less than or equal to 0. So their sum is less than or equal to 0. So this is just generated immediately from the constraints. And now rearranging this, just as we did before, we're going to collect all the terms essentially on x. Okay, and we're going to rearrange this as something transpose x is bigger than or equal to something. Okay, and that is rearranged just by looking that that's going to be minus a transpose u minus g transpose v. This whole thing transpose x. So I move x to the other side. I get this multiplied by x is bigger than or equal to whatever is left here, and that's minus b transpose u minus h transpose v. And this was the game we played in the simple problems as well, where now we try to make this thing equal to the criterion in the primal. So if I can choose u and v such that this thing's equal to c, then this statement is that c transpose x is bigger than or equal to something, and that is the lower bound on our primal optimal value. Okay, right here. So now from this, I can read off the dual, right? Because I have to say I want to maximize this lower bound subject to whatever multiplies x here having to be equal to c. So minus a transpose u minus g transpose v is equal to c. And recall that this was only valid, these arguments were only valid if v was non-negative in every component because of this inequality constraint. So that's my last constraint in the dual. So this is our dual linear program. It's fully general, right? And I can write any linear program in this form. We've just constructed the dual. Okay, so a really interesting example of LP duality is the equivalence between max flow and min cut. And there's a great paper that I list here that gives you the history of essentially these problems in post-World War II. So people like Ford and Fulkerson were working on this problem, and so were a bunch of Russian mathematicians around the same time. And it was a very interesting time, I think, in US history, and also I think the history is something like advances from one camp really spurred advances in the other. And this is where a lot of this was kind of progressed very significantly over a short period of time. There's a really interesting history if you're curious about it. So I'm just going to tell you about max flow and min cut, and I'm going to go through some of the details a bit quickly because you'll do the details on the homework. So the setup is as follows. Let's suppose we have a directed graph whose vertices are v and edges are e. Okay, so I've just drawn a graph here. And we're going to label two nodes of the graph as S and T, which we think of as the source and the sink in the context of max flow or flow. And we're going to define what's called a flow, which is a vector f whose entries has one entry per edge in the graph, fij, to satisfy the following properties. So any vector that satisfies these properties and has an entry for each edge in the graph is called a flow. The first is that it has to be non-negative in every component. So we can only think about essentially pushing, let's say, the flow in the direction of the edges. Right, so we're going to assign non-negative values here. We also have an upper bound of Cij for each particular edge ij. This is called the capacity of that edge. It's a constant, so let's suppose it's given to us. So you think about some design considerations. They say that we have to push things in this direction, but we cannot be pushing more than Cij in this direction. And lastly, this is really the defining property of a flow. If we look at any node k, like say this node, and we look at the sum of all the flows that enter, so the flow from this edge, and this edge, then it has to equal the sum of all the flows that leave this edge. Right, so again, if we think about pushing, let's say, mass or fluid across each one of these edges, then kind of conservation tells us that whatever we put in has to also come out. That's true for every node in the graph except for the source and the sink. Right, the source and the sink, we don't require that to be true. We think about the mass or the fluid emanating from the source and finishing at the sink, so there's no conservation requirements there. Okay, so the max flow problem is essentially just to find, given a graph, the flow. So that means that the vector that satisfies all these conditions and maximizes how much we are essentially able to push out of the source. So maximizes the sum of the flows that emanate from the source. So the sum of fsj for every j such that sj is an edge. So like these edges right here. And you can notice that it's a linear program, right? If I think of f as a variable, this is just a linear function of f. It's just the sum of some of its components. These are linear inequality constraints. These are linear equality constraints. So it's just a linear program. Okay, it's tailored to the graph, but it's still a linear program. So we can derive the dual in a couple of steps. So I'll just do this at a high level, like I said, because you'll do the details on the homework. If you choose to do that problem, you can also choose not to. This is a maximization problem. Okay, so what's different about this versus the ones that we did previously is that we want to find an upper bound on its criterion. Right? Before we were talking about minimization problems, and we wanted to form a lower bound on its criterion. So the dual of a min problem is a max problem. Now we start with a maximization problem, and we want to find an upper bound on its criterion. We're going to end up with a minimization problem. Okay, it's just the mirror image of what we've done so far. So you could negate the criterion, think about it as a minimization problem, and proceed as we did in the previous slides, or you can just kind of flip the logic and the arguments. Either one would work. So we're going to keep it as a maximization problem and just kind of flip the logic and the arguments. Which is, okay, we're going to assign dual variables aij, bij, and xk to each one of these constraints. So aij is going to be assigned to the constraint that fij is bigger than or equal to 0. Bij is going to be assigned to the constraint that minus fij is bigger than or equal to minus cij. And xk we're going to assign to this constraint. Right? This is indexed by k, the node we're looking at. And xk doesn't have any constraints on it because it's it corresponds to an equality constraint, so we don't care about its sign. And if we essentially take an inner product, or if we multiply all those dual variables by all these constraints and add them all up, okay, then we get the following statement. Minus aij fij plus bij times fij minus cij must be less than or equal to 0. That just came from these inequality constraints, multiplying them by the dual variables, adding them up. And if I take the sum of xk times the difference in this constraint, then those are going to add up to 0. Okay, so this is saying the sum of the xk's times the difference in the constraint is 0. And so if we add them all up together, this is less than or equal to 0. That's equal to 0 for flows, for feasible f. The whole thing is less than or equal to 0. Okay? And the criterion, remember, was basically just a sum right? The criterion was basically just a sum of the flows. So we're going to now rearrange all of these terms. I'm just going to express them in quite compact form, so that we're just going to extract all the terms that multiply fij for a particular I and j. And that's going to say that mij, this is going to depend on a, b, and x after we rearrange terms, times fij is less than or equal to everything else. And everything else just comes from this cij times the bij and moving it to the right-hand side. So this is our upper bound, in other words, on the primal criterion, as long as we can make this equal to the primal criterion. Right? This is the same logic as saying, like, if I think of f as a variable, and this is just some vector, I'm trying to get the upper bound, the criterion of my linear program to be upper bounded by something. Okay, and looking back at the criterion, it wasn't actually a sum of all of the fij's. It was just a sum of the fsj's, where s was the source. So that means that a lot of these terms are going to have to be 0. A lot of these multipliers mij are going to have to be 0. In particular, for every I that's not the source, I'm going to want to force mij to be 0. And when I is equal to s, I'm going to want to force mij to be equal to 1. And that'll retrieve this criterion value in the primal. So this is just another way of saying that. If we look at, let's say, all of the msj's, that ends up being, once you collect the terms, the following function of the dual variables, bsj minus asj plus xj. We want that equal to 1. The rest we want equal to 0, because we want to get this to be the primal criterion. So provided that we can satisfy this, we can find a, b, and x that satisfy this, and such that a and b are non-negative in every component. We've just shown that the primal optimal value, okay, or in other words, the maximum flow, is less than or equal to bij times cij, the sum of all those. And the dual problem is now going to be minimizing this upper bound, so trying to get the tightest upper bound possible, subject to those constraints up there, plus the sign constraints on a and b. Okay, and I've just written that here, but I've eliminated a, because essentially a only appears in these equality constraints, and it's constrained to be bigger than or equal to 0, so we can eliminate it by just turning these into inequality constraints themselves. And that leads us to the following problem. Okay, we have two variables, b and x. B is defined over the edges, x is defined over the vertices. We want to minimize this upper bound, the sum of bij times cij, subject to the following inequality constraints. Bij plus xj minus xi is bigger than or equal to 0 for all I and j. B must be bigger than or equal to 0 in every component. Okay, and x has to be equal to 1 at the source and equal to 0 at the sink. So xt is 0, xs is 1. Okay. So just to pause, just as we've seen in the previous examples, this is a linear program. It's the dual to this linear program. Okay. It started off with having one dual variable for every constraint, but then we eliminated some of the dual variables, so now it has fewer. And we know that by construction, if we were to solve this, that's going to be bigger than or equal to the primal optimal value. Okay. The only reason this looked more complicated than what we saw, let's say, with the more general matrix form was because of the kind of specific form of the constraints. This is really no more complicated an argument. It just was that we had the constraints written down in this very specific way. So it made the formation of the dual less abstract and kind of more detailed. But nevertheless, this is our dual problem. Okay. So this itself is not super interpretable. It's not, at first pass, I don't think you would look at this and say, aha, this is min-cut. But let's suppose I told you that at the solution in this problem, okay, when you solve this problem, it just so happened that all of the x's were actually binary value of the solution. So they took either value 0 or 1. Okay, and x is actually constrained to be between 0 and 1 from these constraints. So these constraints actually constrain every element of x to lie between 0 and 1. You can generate those constraints from these ones. And let's suppose that actually at the solution it just happened to be exactly 0 or 1. Then we could actually define two subsets of nodes on the graph of the vertices. We can think about x as an indicator, essentially, for group membership. Let's suppose that the ones for which x was equal to 1 I call group A, and the ones for which x was equal to 0 I call group B. Okay, and I'm going to highlight that in the graph. Let's suppose I solved this problem, the dual of this problem, and I got, let's say x equal to 0 all for these nodes highlighted in blue, and x equal to 1 here. Okay, then if I look at this constraint, Bij bigger than or equal to xi minus xj, right? That's this constraint right here just rewritten. Then this actually reduces to the statement that Bij has to be equal to 1 when I is in A and j is in B. Right? If I and j are in the same set, then this is going to be 0. So this constraint is no different from this non-negativity constraint on B, and I can just ignore it. The only time that this matters is when I is in, let's say, A and j is in B. And then I get the constraint that Bij is equal to 1. Okay, and with that intuition, or with that realization, if I look at the criterion then, the sum of Bij, Cij, that just picks out the capacities that cross the cut. That, in other words, that picks out the capacities Cij for which I is in A and j is in B. So the criterion now just becomes the sum of these edges that start in one group, A, and exit it and enter the other. So in other words, we've just argued that if we looked at the problem where xij was binary valued, okay, then this would be truly the min-cut problem. This is what we'd interpret as min-cut. And what we saw previously here was just the LP relaxation. It's what we get by taking this constraint that these variables, let's say, are equal to 0 or 1, and relax this to the interval 0, 1. Okay, and if we increase the constraint set, that if I make the constraint set bigger in a minimization problem, then the minimum can only get smaller. Right? So if I look at min-cut, let's say, the min-cut problem, and look at its LP relaxation, then the optimal value in the min-cut problem can only be bigger than or equal to the optimal value for the LP relaxation of it, right? Because this is solving the same problem over a bigger domain. Whereas the previous set of arguments that we've just made actually, by construction, showed us that this thing upper bounded the value of the max flow. Right? This was just duality. So we have this hierarchy of inequalities. Max flow is less than or equal to its dual criterion, which is in turn less than or equal to min-cut. This dual being the relaxation of min-cut. And there's a very famous result that's due to Ford and Fulkerson called the max flow min-cut theorem, which says that actually these two are equal. The capacity of the min-cut is equal to the value of the max flow. Those are equivalent. And now that tells us that actually all of these inequalities are equalities. Okay, so in particular, in this problem, that implies that this relaxation, well, it implies two things actually that are interesting. The first is that this relaxation is tight. So min-cut, although it's combinatorial and non-convex, it's actually equal, it's equivalent to its convex relaxation. That's the first realization. The second realization is that the dual here is tight. So these two are equal, meaning that our dual construction gave us exactly the same criterion value. Okay, and that was a much more sophisticated example of strong duality. That's the name we used to apply to the case in which the dual is tight, over top of something like this, which we saw we had strong duality in simple problems like this. So as I said, we're going to see how often this happens when we talk about, I think it's duality next time. So this seems to be a good place to take a break. Let's take a break, and we'll come back and talk about the rest. We have just a couple more things, and I wanted to spend enough time on the last example because I think it's really cool. I'm going to start off by giving you another perspective on LP duality. Okay, it's a different way of deriving the same dual, the same result. And the arguments here are actually, in some sense, preferable as we move forward to convex problems that are not linear programs, because they're general. So we start off with this primal, right? And here's another explanation for how I can end up with this dual. I'm going to form something that I call the Lagrangian. And by the same arguments that we already gave, actually, this thing is less than or equal to 0 for any feasible x, as long as I take v to be bigger than or equal to 0 in each component. This is the same argument that we used essentially last time, right? If u is anything and x is feasible, this is 0, so this whole thing is 0. And if v is, let's say, non-negative in every component, and x is feasible, then this thing is less than or equal to 0 in every component. So taking inner product with v, which is bigger than or equal to 0 in every component, results in something that's less than or equal to 0. Right, so this whole thing is less than or equal to 0. So if I add it to c plus c transpose x, then I can only make it smaller. Right, so c transpose x is bigger than or equal to c transpose x plus this whole thing. This is a function of three things we can think about: x, the primal variable, and u and v, the dual variables, that we call the Lagrangian. And from what we've just argued, right, for any u and any v that's bigger than or equal to 0, if we were to minimize this, let's say, over the feasible set, call the feasible set capital C, that gives us f star, the primal criterion value. And that is bigger than or equal to the minimum of this over the feasible set, the minimum of Lxu over all x in the feasible set, right? Fixing at the moment to any u and any v that's bigger than or equal to 0. So this just comes by minimizing both sides with respect to x over the feasible set. Okay, if we drop the constraint that x is in the feasible set, capital C, then that can only make the minimum smaller, right? And minimizing over a larger space, I can only get something that's smaller. That's the minimum of the Lagrangian over all x unconstrained. And this is now only a function of u and v, which we call g uv, right? Because I've minimized that over x. What happens if you were to try to minimize this over all x without any constraints whatsoever on x? Well, there would be two cases. One case is that it just so happened that when you wrote this as a function of x, whatever multiplied x, that term, transpose x, was 0. Okay, so then it was a constant, and minimizing out over x, you just got that constant. That's case 1. Case 2 is that that doesn't happen. So it's actually a linear function of x, right? U and v aren't arranged so that that term is 0. It's actually just something transpose x. And in that case, if I minimize that over x, I get minus infinity, because it's a linear function, right? So if I'm minimizing a linear function that's non-trivial, then I get minus infinity. So in other words, this GUV function, there's only two cases. The one case is that if we write this as something transpose x, that something ends up being C plus A transpose U plus G transpose V. And if that thing happened to be 0, then minimizing it over x only gives us the constant term that doesn't depend on x. Oops, that's all the terms here that don't depend on x. That's just this minus B transpose U and minus B transpose H. If that doesn't happen, then I just get minus infinity. Okay, so this function, we can think about, it has a domain. It's a function of u and v, and it has a domain that is specified by this constraint. It's minus infinity outside of this constraint. So I can think about maximizing this function over all u and over all v that are bigger than or equal to 0 in each component. And this is going to give me the tightest lower bound on my primal criterion value, right? Because it's a lower bound for any u and v, and so maximizing gives me the tightest lower bound. Taking a look at this, maximizing this function over all u and v being equal to 0, that is exactly this dual. Okay, we've just arrived at the same answer, but with a different sequence of arguments. Okay, maximizing this function subject to this equality constraint in v bigger than or equal to 0. So this is less, I think it's actually less constructive in some sense than the LP duality version that we looked at already, but it is much more general. It's called Lagrangian duality, and it applies to really arbitrary optimization problems, even non-convex ones, but of course for the most part next time we'll talk about convex problems. Okay. So let's enter this last example. I think it's a pretty interesting example. It's another application of LP duality. And here's the setup. Let's suppose that there's two players. Okay, there's me, and then this other guy. Who is this person? Do you guys know who this is? Wow, von Neumann, you guys are great. Yeah, I wasn't sure that people would know. Okay, so yeah, he's obviously well known. And let's suppose there's a payout matrix, P, and we play according to the following strategy. Okay, so basically I have, R has n options to choose from, and J, his first name is John von Neumann, has m options to choose from. And I pick an option, J picks an option, and we then look up the following entry in this payout table. Let's say P21, and J pays that amount to R. So this amount could be positive or negative, right? So if P21 was positive, then I would be earning money, and if it were negative, then I'd be losing money. Okay? So we think about the payouts going from J to R, but they're also signed, so it's not like it's unfair. It's just it's the way we're thinking about it for simplicity. Okay, and let's suppose further that we use what's called mixed strategies. So we're each going to actually choose a distribution over the entries that we can choose. We're going to form a distribution over the entries that we can choose, and we're going to pick a strategy an option according to that distribution independently. So we're once we form distributions, we actually each generate our options independently. So he forms a vector x, okay, with entries xi, and that specifies the probability that he would choose any of his options I. And I would form a vector y, and yj would form the probability that I would choose any of my options j. Okay, and so of course these have to be non-negative and sum to 1. They're probability distributions. Okay, and in this setup now, we're going to think about kind of what are the optimal strategies either person could take. So we're going to look at the expected payout. That's a good metric to look at, which is just the probability that you know, let's say R would choose, or J would choose I, and R would choose J, times the payout for that combo, okay, summed up over all the options. So this is the expected payout, which I can more succinctly write as X transpose Py. Right? P is the payout matrix. X and Y are betting strategies, the probability vectors that specify our strategies. And so the expected payout from J to R is X transpose Py. Okay, so let's suppose that von Neumann he's smarter than me, and he's say, I'm going to do you a favor, and I'm going to let you know my strategy ahead of time. So I'll give you X. Okay, so I'm thinking about now looking at von Neumann's strategy X. I want to choose my strategy Y to maximize the payout that's coming to me. Okay, so given X, I want to actually maximize over all Y, X transpose Py, subject to Y being a probability vector. Right? Bigger than or equal to 0 in every component, and the sum of the Y's is 1. Okay, and if you just look at this, then this is, right, just saying that I want to maximize C transpose Y, right, subject to these simplex constraints. And the answer is find the C that's largest and put all your mass on that C. That's it. Okay, and C is just P transpose X for us. Right, so this is going to equal the maximum of the CIs. That's what this maximum is going to equal, the maximum value. Right, because I'm going to choose Y to be putting all my mass on just the biggest entry of C. And in other words, the payout I should expect if I play my best strategy, and von Neumann tells me his, and that's X, is this thing, the maximum over all I of P transpose X, the ith component of P transpose X. Okay, so this would be my expected payout if I play optimally. And of course, von Neumann's very wise, and he's going to know that I'm going to do this calculation. Okay, and he's going to say that, well, I'm going to actually now choose my X to protect against this. I'm going to minimize the optimal payout that Ryan's going to receive over all X. So I'm going to form X such that if Ryan played optimally, then I would be forced to give him the smallest payout. Right? Min over X of this payout, max over I, P transpose X in the ith component, subject to X being in the probability simplex. Okay, so this would be essentially his payout to me if he played optimally and I played optimally in the scenario where I knew his strategy. So it seems still like an unfavorable strategy to him, right? An unfavorable scenario to him. He's going to reveal his strategy, and we're both going to play optimally, and this is going to be the expected payout. Now let's suppose that somehow the universe were reversed, and von Neumann actually, should be pitied, and I was deciding that I would give him my strategy beforehand, and that he would be the one who got to pick based on my strategy. Then by the exact same logic, the payout from von Neumann to me, if we both played optimally, but he knew my strategy ahead of time, would be given by this optimization problem. The max over all y of the min over all j of py in the jth component subject to y lying in the probability simplex. Okay? So now we have two problems. These are actually linear programs, by the way. They're not obviously linear programs written like this, but we could introduce, let's say, additional variables to make them linear programs, which we'll do shortly. And one describes the payout under optimal strategies from von Neumann to me if he revealed his strategy ahead of time. And the other describes the payout from von Neumann to me if I reveal my strategy ahead of time. Okay, so let's call the first one F1 star and this one F2 star. So because it's clearly advantageous to me if I knew von Neumann's strategy versus he knew mine, F1 star should be bigger than or equal to F2 star. Right? Whatever payout I'm going to be receiving in either situation, it should be better in the first because I'm the one who's aware of his strategy ahead of time. And in the second, it's the opposite. So we have this ordering. You know, this is kind of, let's just say, clearly true based on the fact that it cannot be worse for me to know his strategy. And there's a very famous theorem called von Neumann's minimax theorem. It is essentially LP duality. I mean, we can prove with LP duality. That says that actually these two are the same, the exact same value. So under optimal game playing, it doesn't matter who knows whose strategy first. It's the same result in either case. And I think this is actually a very kind of surprising result. So we're gonna prove it just using LP duality. Okay, so looks like I missed a criterion here. I don't know why I did that. So let's start by, we said, recasting just this first problem. So min over all x, max over all p transpose x and the ith component, subject to the constraints x being bigger than or equal to 0 and 1 transpose x being equal to 1. Okay, let's introduce another variable t. So t is just going to be a scalar. And we're going to just call the criterion t. And we're going to introduce a constraint, which is that max over all I, p transpose x I is less than or equal to t. Okay, so this is going to be just a reformulation of our problem. Right? These are equivalent because I would never take this inequality to be loose. There would be no reason. So at the solution, this is going to be an equality, and I would get back as the criterion just the max of p transpose x. And this is another way we can just formulate this is that p transpose x should be less than or equal to t. So this is just if the max of the entries of this vector is less than or equal to t, then it's the same as saying every entry of the vector is less than or equal to t. And this is just our notation for that, right? We often use this notation in this class. So that's a reformulation of this problem, and now you can see it's an LP, right? Because I have linear constraint in the linear criterion. It's actually just the last part of my optimization variable, thought of as a big variable, x comma t. This should say x. I don't know why I wrote y here. These are linear inequality and equality constraints on my variables, and these are more linear inequality constraints on my variables. It's just an LP. So let's do form the dual via Lagrangian duality. Okay, you could do it either way. You could also use LP duality that we talked about at the start of the lecture, but because we're moving towards this from now on, let's form the dual using Lagrangian duality. So the workflow is we write down the Lagrangian, okay, which has our primal variables, and then it has a dual variable essentially for each constraint. So I called that u, v, and y. And I called this y actually for a very particular reason. You'll see in a second. And u is going to correspond to this inequality constraint, v to this equality constraint, and y to this inequality constraint. So the Lagrangian is, remember, it's t, it's the primal criterion. And here it's going to be minus u transpose x, right? Because I can think of this as minus x being less than or equal to 0. Take an inner product with a u that's non-negative and a y that's non-negative as well. Okay, the next piece is going to be plus v times we can write 1 transpose x minus 1, or in the slides I guess I wrote 1 minus 1 transpose x, but they're equivalent. And the last piece of the Lagrangian is going to be y transpose p transpose x minus t, but I'm going to write t times the 1's vector, because to make this a vector, I'll just think about this as, it's t in every component, so t times the 1's vector. So this is the Lagrangian. It's defined, it's well defined, let's say, for u that's bigger than or equal to 0 and y that's bigger than or equal to 0, and there's no constraints on v because v corresponded to this equality constraint. Okay, and now I'm going to define the Lagrange dual function. It's a function of u, v, and y given by minimizing L, x, t, u, v, y over all x and t unconstrained. Okay, so let's just rearrange terms. Let's get all the terms that depend on, let's say, x first. So I get minus u transpose. Here I get minus v times the 1's vector. And here I get p times y. So all the terms that depend on x are py minus u minus v times the 1's vector. Okay, that's what I have multiplied by x. And all the terms that depend on t, that's just t. And I have minus y transpose the 1's vector. So it's just going to be 1 minus y transpose the 1's vector times t. Okay, so minimizing this over all x and t, it's either going to be, there's going to be two cases. Oh, sorry, there should be one other term, right? There's still a v floating around. I don't have, that doesn't multiply either x or t, but it's still part of this Lagrangian. So there's two options. The one option is that this minimum is equal to v, and that's true when both these leading terms are 0, because then it's not a linear function, it's just a constant. So if py minus u minus v times the 1's vector is 0, and 1 minus y transpose the 1's vector is 0, then we get v. Otherwise, we get minus infinity. Right, because I can make this arbitrarily small. And that was my dual function. And if I want to get the tightest lower bound, okay, if I want to get the very tightest lower bound, then I'm going to maximize the dual function, right? So the dual of my LP that we had, right? This is the LP that corresponded to the payout in the first situation, this one here, this LP here. The dual is just given by maximizing this function, which we can write as maximize out over all u, v, and y. V, right, subject to py minus u minus v1 equals 0. 1 minus y transpose 1 equals 0, u being bigger than or equal to 0, and y being bigger than or equal to 0. Okay, and there's no purpose really to have u around. Okay, I can eliminate u by writing this as max over all, let's say, v and y, v subject to py is bigger than or equal to v times the 1's vector. Right? Because if u is bigger than or equal to 0, I can turn this equality constraint into this inequality constraint. And the same constraints on y and v. Or really just on y at this point. Okay, but now look at this. This is just the LP reformulation of the second problem we're looking at, right? If I tell you that you can just work backwards. If v is smaller than or equal to py in every component, then that's the same thing as saying that the min over all I of py times I is bigger than or equal to v. Okay, and for the same reason as we argued last time now, I can eliminate this v. I mean, the last time we actually introduced a slack variable, now we're eliminating the slack variable. So we're moving from the LP formulation to the min-max formulation, or here it's a max-min formulation. Right? This is equivalent to maximizing the minimum of entries of py subject to y being in the probability simplex. Okay, so in other words, we've just shown that that these two problems, this problem and this problem, are duals. Okay, that we can get one from the other just via Lagrangian duality. Okay, and because in fact they're both LPs, because in fact they're both LPs, and I told you that linear programs essentially always have this tightness of the dual, we get strong duality, which means that these two criterion values match. So somewhat remarkably, this was, I think, a kind of a surprising result in game theory at kind of the birth of this of kind of understanding of minimaxity in this area. It doesn't really matter who knows whose strategy. Under optimal playing, it ends up being the same. And von Neumann is famous for many things. He's famous for this as just one of them. But interestingly now, we've seen that there's like two results that are quite famous that are just LP duality. Maxwell min-cut and also this minimax theorem. Okay, and so I've been wobbling about when you're going to learn about strong duality. I just checked in the break. It is next lecture. So we'll talk next lecture about Lagrangian duality, and we'll also tell you about when the dual is tight, which is called strong duality. And I will see you guys then.